Hello, today we are looking at topic 213, exponential and logarithmic equations and inequalities. So we're going to start today off by doing a little bit of a warm-up. These are examples of exponential equations that you learned how to solve in Algebra 2. And so when we learned how to solve these, then we did that by trying to make the bases the same, because if we can make the bases the same, then we have the property of equality of exponents that says that if the bases are the same, then that equal sign in the middle means that the powers also have to be the same. So go ahead and pause your video and work through these four problems, making the bases the same for each time so you can equate the exponents and solve the equation for the exponential models. Go ahead and pause. Okay, so let's look at the first one, see how you did. The two sides of the equation have one power on each side. The base on each side is 2, so I don't need to change the base. I can just simply equate the exponents. So I pull those exponents off, set them equal to each other. I move the 2 over here with the 5x to get 3x, and I move the 1 across the equal sign over here, so 7 plus 1 is 8. And I want to get x by itself, so I need to get rid of the 3. So I divide both sides by 3, and x equals 8 over 3. And remember, your answer should be the last thing I see in your work. There should not be any need to box it. The work should go vertical, not side to side. I don't want to see anything here with an arrow and an arrow and an arrow and an arrow. Make sure by now we're halfway through the year, we should be doing our work vertically without having to think about it. All right, so this next one, we have one power on this side that has a base of 8, one power on this side that has a base of 2. I can rewrite the number 8 as a power, 2 to the third power. So I do 2 to the third power times the exponent that's already there. So that's 3x minus 2. I didn't need to change this side because it was already base 2. So now I simplify my numerator. So I take 3 times 3x, which gives me 9x, and 3 times negative 2, which gives me negative 6. Now I have one power on each side having a base of 2. So the property of equality with that equal sign in the middle means what is on this side is exactly the same as what's on this side. So if this is 2 and this is 2, then I can equate the exponents and say 9x minus 6 has to equal x plus 5. And so then it's just a matter of solving this linear equation. I'm going to move the x over here with the 9x, and that becomes 8. I'm going to move the negative 6 over here with the 5. That becomes 11. And to get x by itself, I divide both sides by 8. So x is going to equal 11 over 8. Try to make sure your fractions have that horizontal bar and not a slash. Make your life easier if you're in the habit of that now. All right, let's look at E. Let's see. So this is a 9 and this is a 27, and they're most definitely not the same base, but we can make them the same base of 3 because 3 squared is 9 and 3 cubed is 27. So once I rewrite those with a base of 3, then I clean up the exponent because 9 became 3 squared, but there was already a 2x in the power as well, so that's 2 times 2 times x, or 4x. And here I have to distribute the 3 through, so I get 3x plus 6. So since the bases, one base on each side is equal, 3 and 3, then the exponents have to be equal, so I can equate them. I can pull them off. I'm going to move the 3x over here with the 4x so I can keep my x's positive, and that means x equals 6. And finally, we have a fractional base, so we know that we can make that change its position in the fraction and become a negative 1 times the 5x plus 7 that's already there. So I distribute the negative 1 through the top, and I now have in the exponent negative 5x minus 7. So I have a base of 2 on this side. I have a base of 2 on this side. So with the property of equality, I can equate the exponents. So now I know that negative 5x minus 7 is equal to 2x. I'm going to move the negative 5x over here with the positive 2 to give me a positive 7x. That means positive 7x equals negative 7. So to get x by itself, I'm going to divide both sides by 7. Negative 7 divided by positive 7 gives me a negative 1. And so those are my solutions for my exponential basis. So that was just a reminder and refresher of what you learned in Algebra 2 last year. This time around, we're going to talk about solving exponents and logs. I'm focusing a little more on solving the logs today. Okay, so after the warm-up, now we're going to look at solving equations and inequalities, focusing mostly on the equation work today. because once we know how to do the equation, we know that inequalities are just a matter of setting up your plus minus number lines and figuring out when it's greater than or less than, so you can get your solutions, because inequalities have multiple solutions, so that makes them different. So we're going to have intervals of numbers that represent the solution. So we've worked with exponential functions and logarithmic functions. We've looked at important properties. We've looked at how to find equivalent expressions. And now we're going to use all those same properties to solve equations and inequalities. That's kind of the whole focus of this lesson. So let's review a couple of properties of exponents. We know that we have the product property, where if I multiply like bases, I can add the exponents. We know we have the power property, which is where I have a base with a power raised to another power. So this is multiplication or repeated addition, so you can just multiply those exponents there. We have reviewed this year the negative exponent property, which says that we can change a number's position in the fraction by moving it. So this would be the same thing as b to the negative n over 1. So then I can move it out of the top and down to the bottom, and it becomes positive. We have also studied properties of logs, and we talked about these in our last lesson. We have the product property, which says that if the argument is a product, I can expand that into two separate logs, or however many factors there are, however many logs I'm going to have. Every one of these log base b becomes part of each expanded term. So the product property reminds you that the argument is a product, and the connector that we use to pull it apart or put it back together is an addition sign. We learned about the quotient property, or actually we just reviewed it because you did learn that one in Algebra 2, and that is a log that has a quotient that is a division problem. And when that's the case, you can expand it back out with your subtraction symbol. Each of the expanded terms has a log base b in it, and then each term contains part of the fraction. And remember that order matters, so we always subtract top minus bottom. All right, and the third property we reviewed in the last lesson was the power property. And the power property means inside the argument there is a power, and if there's a power inside the argument, you can drop it in front of the log and make it become a multiplier. We have also looked at converting between exponential and logarithm forms. And so that means if it's an exponential form, it's a equals b to the c. If it's logarithmic form, it's log base b of a equals c. Remember, the output to a log is the power. So using all of these properties today, we are going to look at what some different solving situations are going to look like. So the first process that we're going to look at in terms of solving log equations is the process when there is only one log expression in the function. So only one log. When that's the case, to solve it, we're going to convert between exponential and logarithm forms. So here are our steps. We're going to isolate the exponent or log onto one side of the equation. We're going to write the equation to the alternate form. So if it's exponential, we're going to go to log. If it's log, we're going to go to exponential. Then we're going to solve for the variables if necessary. And then we're going to simplify and round answers as directed. So if it's one where we're going to be rounding, then we definitely will have that there. So example 1, solve the following equations. Leave your answer in exact form. All right, so we're solving the equations. We're leaving our answer in exact form. That means there's not going to be a decimal equivalent. And so let's start with this first one that has an exponent. So the first thing that we're going to do here is get the exponent where the variable is. See how the variable is in the power? That's the piece that we want to isolate in step 1. So that means I'm going to move the 2 to the other side, which is a 9. So now, in order to get the power, unknown power, the variable in the power, out of the power, we're going to convert it to the form. So we know that the output to a log is the power. So I'm going to say x equals, and then I'm going to have log, and then what's the base of the exponent? It's a 4, so that's going to be the base of my log. And then that leaves the argument to be here, which is 9. So technically, by rewriting it, I did solve it. I don't know, without using a calculator, what log base 4 of 9 is, so that is, in fact, the exact form. All right, so let's look at the next one. So here is my exponent where the variable is up in the power. So this is the term that I need to get by itself, just like it was here. This is what I'm isolating. So I'm going to take 2 to the x plus 3 equals, I'm going to move the 5 over to the 26. So 26 minus 5 will be 21. Now, to get the variable out of the power and down into the problem so I can work with it, I'm going to put it in its alternate form. All right, so I have log, what is the base of my exponent? That's 2, so that will also be the base of my log. And then the output to a log is that whole power of x plus 3. That means my argument has to be the 21. So I haven't solved this because what does solving mean? It means that we are isolating the variable, solving for the variable, simplifying anything that needs to be simplified. So to solve for the variable, I'm going to get x by itself. So that's x equals, I'm going to move the 3 over here with the log. So that's going to be log base 2 of 21 minus 3. Now notice this, the argument of the log is what's stuck to the log. So this means minus 3 at the back. It's not parentheses around 21 minus 3. It is just a vertical shift down of 3. So that's what x equals. All right. So now let's look at C. So here is my exponent that I'm trying to isolate. So I want to get that by itself. So I'm going to move my 3 to the other side. So negative 7 minus 3 gives me negative 10, and I have negative 4e to the x. So now remember, I'm trying to get e by itself, and I can convert between forms once I have the e by itself, but I still have this negative 4. So I'm going to divide both sides by negative 4. That's going to give me negative 10 divided by negative 4, or 10 over 4, equals e to the x. So once I have that, then I can convert it to a log to get to the power, which is where the variable is. So for me, then that's going to be natural log, and it's base e because that's base e. And then what does that equal? That equals the power. So there's going to be my x. And how does the fraction 10/4 simplify? To 5/2. And so that's what solving is going to look like. So those are examples of solving an exact form. And now we're going to solve the following equations, again, in exact form. Well, notice that these ones we're practicing right now are logs, and to get the log by itself is what we're isolating. So for instance, if I look at this one right here, this is where my log is right there. So that's what I need to isolate. So remember, we are isolating the exponent or the log, then we're writing the equation in the alternate form, then we're going to solve for the variable and simplify or round answers as directed. And in this case, we won't be rounding because the directions say to give our answers in exact form. All right, so let's do one together, then we'll pause your video and see how you do on B and C. So the first thing I'm going to do is I'm going to move the 4 over with the 10. So I have 2 log base 3 of x plus 3. Remember your parentheses around the x plus 3 because all of this is stuck to the log. And that's going to equal 10 minus 4, which is 6. And now I need to get rid of the 2 that's still attached to my log. So I'm going to say log base 3 of x plus 3. And then I'm going to divide this side by 2 to get rid of that 2. And what you do to one side, you have to do the other. So then I'm going to take 6 divided by 2. And 6 divided by 2 is 3. So once I have my log isolated, then remember, we rewrite it in its alternative form. So the base of the log is 3. So the base of the exponent is going to be 3. The output to a log is the power, so that means it's 3 to the third, and the output for that exponent is going to be the argument, so x plus 3. So I have 27 equals x plus 3. To get x by itself, I'm going to move the 3 across, and 27 minus 3 is 24. So that's the gist. So go ahead and pause your video, work through B and C, and we'll come back and compare. Okay, so here's what I'm trying to isolate. So I moved the 2 over with the 4, so 4 minus 2 is 2. Now I've isolated my log, so I'm going to rewrite it in its alternative form. So that's 5 to the power of 2 equals the argument. And then 5 squared is 25. So I'm going to get x by itself by moving the 1 over here and doing 25 plus 1 is 26. To get x by itself, I need to divide both sides by 2. 26 divided by 2 is 13. Over here, what needs to be isolated is in the top of my fraction. So I'm going to get rid of the bottom of my fraction by multiplying both sides of the equation by 5. And so I have this 5 and 5 here, which just leaves me with ln of 2 minus x, keeping your parentheses around the 2 minus x, equals 5. So now I have it isolated, so I can change forms. So what is the base of natural log? It's e to the output, which is the power of 5, equals the argument, which is 2 minus x. So to get x by itself, I move the x over here to this side with the e to the 5th power to make it positive. And then I subtracted e to the 5th power to the other side, so that x would be by itself, which means x equals 2 minus e to the 5th. So hopefully you kind of have the process. You can see 3 where they're in exponential form. You can see 3 where they're in log form, and those answers are given in exact form. So you don't need any kind of calculator to be able to answer these questions. Okay, so now we're going to look at the process when we have more than one log. So in the last set of instructions and the process that we used, we said that we're solving when we have only one log or only one exponential function. The warm-up, we had 2 exponential functions that we could put one on each side of the equal sign, and then we could mathematically make the bases the same. Here, we only have one log statement or one exponential statement. So one exponential statement or one log statement. But that's not the only kinds of problems that we have. So this is the process we're going to follow when we have multiple logarithms. Okay, so we're going to use the log properties to simplify the expressions before we begin solving the equations. So we're going to simplify the expressions before solving the equation or the inequality. And this equation will generally simplify to one of 2 forms. We have form 1, where we can simplify it down to a single log on one side. Or we have form 2, where we can simplify it down so we have one log on each side of the equal sign. So here, one log on one side of the equal sign. Here, 2 logs on each side of the equal sign. Okay, so if it's form 1, then we can finish solving by converting the exponential form as we did in the example 2. So in other words, we get to this point, we can do what we've been practicing. If it's form 2, however, it's not going to simplify into this form. So we finish solving by setting x and the y equal to each other. And this is an algebra 2 property of equality of logarithms, which basically is what we've talked about before. If you have this log, whatever the base is, crossed on the other side of the equal sign, you have the exact same log with the exact same base, then for this equal sign in the middle to be true, this x and this y have to be equal to each other. So that x and that y is what we're talking about right here when we say set x and y equal to each other. So again, nothing new. This is just reviewing and refreshing your memory about the things that you learned in Algebra 2. So 2 important notes to keep in mind here. In either case, we do need to check for extraneous solutions. Why is that important? Because when we're working with logs, sometimes through no fault of our own, we can perform all the mathematical operations, but because there are restrictions on the domain and certain things that logs can and can't do, sometimes those solutions we produce when we check them in the problem, they don't work. They're not in the domain of the original equation. So we always want to check that domain and make sure when we get an answer that it's going to fit in the problem. Then the second thing is when we have all of these logs, log of x plus log of y equals log of z, then we need to keep in mind that doesn't simply mean we can just cancel out the logs and do x plus y plus z. It is not implied that you can do that. In fact, you can't. So remember, we can use our condensing rules to condense down. So I have one log on each side, but just because they all happen to be the same logs doesn't mean I can just get rid of them and have x plus y plus z. We must use log properties to simplify. You cannot just cancel out the logs. Okay? So that's a big no-no. So make sure that you don't fall into that trap. Okay, so remember that these are multiple logs that can either condense down to a single log or can condense down so there is one single log on each side of the equal sign. All right, so we're going to solve the following equations, and then we're going to check for extraneous solutions where necessary. So the first thing that we're going to do here in this problem is we're going to look at those arguments and make sure we know what x can't be. For instance, right here, this one has been shifted to the left 4. So our x's for this have to be greater than 4. Over here, this has had several transformations, but in essence, I just kind of want to know the domain where it's shifted to. So if I solve this equation, I can say 5x minus 2 equals 0, move the 2 to the other side, divide both sides by 5. So what that tells me is my x's here have to be greater than 2/5. Okay, so we move the 2 over and we divide it by 5. So when we get to checking our answers, we're going to use those facts to help us check out the answers. So I usually try to go ahead and establish that before I start a problem, then I don't have to worry about that later on. Okay, so we have multiple logs on this side and a single log on that side. So remember, multiple logs mean it's either going to simplify to one log, which is probably not going to happen because we have all of these. So we're looking to make it look like this. So I'm going to take and use my condensing rules on the left-hand side to simplify that down. So the log for this particular problem is log base 10. And then inside the argument, since it's connected by a plus sign, is going to be a product. So I'm going to have 3 times x plus 4. Okay, so once I've condensed this side down, excuse me, I'm going to simplify in here. So I have log of 3x plus 12 equals log of 5x minus 2. So that's the first thing I did is I condensed down and got everything put together. So now it looks like this property, which says log base a of x equals log base a of y. So if the log on this side is base 10 and the log on this side is base 10, because of that equal sign in the middle, then this is my x and this is my y. So according to this rule up here, now I can say x equals y. That's called equating. So I can pull that x and that y out, and I can solve for x by solving this equation. So let's see. I'm going to, I think, move the 3 over to the 5 so I can keep my x's positive. So 5x minus 3x is going to give me 2x. And then I'm going to have to move the 2 to the other side. So add 2 to both sides gives me this side to be 14. And then to get x by itself, I'm going to say x equals 14 divided by 2, which is 7. So now I need to check. So I'm checking this argument and seeing 7 plus 4. That's not going to give me anything weird here. 3 times 7 minus 2. It's not going to give me anything weird right here. So once I know that if I plug this value into the arguments are okay, then I need to make sure this is going to fall in the domain of the function. In other words, there aren't any places where this wouldn't work. So as I'm checking here, I'm thinking these have to be x's greater than 2/5, and it is. This has to be an x greater than 4, and it is. So this one would check out because I checked each individual argument, and then I checked to make sure it was falling within the domain. All right, so the next one is the same type of problem, but it's natural log. So I'm thinking about in here, x plus 1 equals 0, so I want x's greater than -1. And over here, I need to know when that is going to shift. So I'm going to say the x's, and I'm going to move 5 to the other side, divide by 3. So these are going to be bigger than 5/3, and that's a number, so I don't have to worry about that. So then as I'm trying to figure out which part I'm going to do first, over here I have multiple logs on the left, a single log on the right. So this is the side that I'm going to condense. So I condense both of these with the natural log. Its connector is subtraction. So natural log, and it would be the first one divided by the second one. So now that's my argument, and that equals natural log of 7. So now I have established this property where I have one log over here, which happens to be natural log base e, and one log over here, which also happens to be natural log base e. So those are the same logs, which means according to this equal sign, then I can equate the arguments. So I'm going to have x plus 1 over 3x minus 5, and that's going to equal 7. So now I'm going to go about the process of solving for x. So I'm just going to multiply both sides by 3x minus 5. So I'm going to have x plus 1 equals 7 times that 3x minus 5. And then I have x plus 1, so I can distribute. So I get 21x minus 35. Then I can get my x's together, and you can move them either way. I'm going to move my x over here with 21. So on this side of my equation, I get 21 minus 1, which is going to give me 20x. And then that means I'm moving the 35 over here, so I'm adding 35 to both sides. So this side is going to equal 36. And then to get x by itself, I'm going to take 36 and I'm going to divide that by 20. So that's the same thing as x equals 9/5. And so now I'm going to check it to make sure that it's going to work out. So I know if I put 9/5 in here, 9/5 times plus 1 is going to give me a number that is bigger than -1. And if I put 9/5 here, so I get 3 times 9/5 minus 5, which is going to give me a value bigger than 5/3. So I know that it works here. So I can say that I overall have checked that one out. All right. So as I kind of worked an example of each, I would like for you to pause your video now and practice what we've just been working on with examples C and D. So go ahead and pause your video. Okay, so on this one, we checked the argument here, so we know that x has to be greater than -2 because this is just horizontally shifted to the left, -2. We knew here it had to be greater than 3 because this is shifted to the right, 3. So there are my multiple logs on one side, so that's what I'm going to condense. Be really careful with your notation because it's both of these things multiplied together that produces that argument. So once I have one log on each side, so this is definitely a case of form 2, then we can equate the x and the y. So here I have set it equal. Factored this out or multiplied it out, however you want to think of it. I got x squared minus x minus 6 and a 14 on this side. So I need to move the 14 over here with this -6. So subtracting 14 and a -6 gives me a -20. This is a factorable trinomial, the factors of 20 that subtract and give me -1 are -5 and 4. And so then that produces a possible solution of x equals 5 and a possible solution of x equals -4. So then we have to check to make sure these fit up here in our areas. So 5 is definitely bigger than -2 and definitely bigger than 3. So that one checks out. When I put the -4 in here, I get this misstatement. -4 is not greater than -2. Therefore, it means that this problem can't be a possible solution or an actual solution because -4 is actually less than -2, not greater than. So the only solution on part C is at x equals 5. Okay, let's look at the natural log. So the natural log, this base has to be greater than 0. So I can condense this side down to a single natural log of an argument with x over 3. And now I can rewrite it. So this is a case of form 1. So the base is e to the power of 2 equals x over 3. So to get x by itself, I need to get rid of the 3 down here in the denominator. So I multiply both sides by 3. That makes my left-hand side 3e to the 2 equals x. This is just a constant. E squared is a little bit bigger than 7. So if I do that, 7 times 3 is definitely going to be a number bigger than 0. So then my only solution for this particular problem in D is at x equals 3e to the power of 2. So we had a solution on A of or at x equals 7. We had a solution for B at x equals 9/5. We had only one solution on C at x equals 5. And we have a solution here at x equals 3e to the second. So remember again, this is just a number. E squared is a number a little bit bigger than 7, somewhere around 7.3 times the 3 just produces a number here. So that's my solution. Okay, so that's our problem wrap up for example 3. Now let's take a look at example 4. Okay, so in example 4, we are still solving the exponential equation, and we are still checking for extraneous solutions when necessary. So nothing has changed here except that we have to look for, it looks like we have maybe the power here too. So we're going to bump that 3 back up to the 2. Again, condense this side, use the second form. Over here, I can't get just one log on each side. That pesky 2 is in the way. So I'm going to have to rewrite this so I have both of my logs on the same side and set it equal to this constant number. And so this one is going to look more like form 1 when I'm finished. I move the logs to the same side, condense them down to a single log. So form 2, form 1, go ahead and pause your video. Don't forget to check for extraneous solutions, and we'll come back together here in a moment and check and see how you did. So go ahead and pause your video. Okay, so on this one, remember when you have powers, then you're going to have to use the power property first. So we're going to bounce that 3 right back up into the argument because that 3 is the power of the 2 that's in the argument. Okay, so I have log base 4 of x minus log base 4 of 2 cubed. All of this is the argument, not log base 4 of 2 to the third power. So keep in mind it's in the argument. That equals the right-hand side, which is log base 4 of x plus 7. So now that I have these two properties on this side, then this is what I can condense right over here. And so I do that condensing through the quotient property. So it's x divided by 2 cubed or 8. Now I have one log on both sides, so this is form 2. So that means I can equate my logs. So x over 8 equals x plus 7. So I need to get my x's together. So I need to get rid of this 8 that's down in the denominator. So I'm going to multiply both sides by 8. And that means over here I have 8 times x, which is 8x, and I have 8 times 7, which is 56. So now I need to move the 8x over with the x. So I need to isolate. So subtract 8x from both. Well, actually, I tried to keep it positive. Let me backtrack. I I move the 8 over here to keep this positive and keep it isolated. So that's where my 7x comes from. And so when I subtract 1x here from my 8, I get 7, which means I have to move 56 to the other side or subtract 56 from both sides. So that becomes negative 56. So to isolate x, I'm going to divide both sides by 7, which gives me negative 56 over 7, which is 8. And then as I'm checking, remember I'm checking it into the condition for this log, which means x has to be greater than 0. And it's not. Negative 8 is actually less than 0. So that part doesn't work. And I really don't have to check anywhere else. But I went ahead and checked this one too, just because I wasn't 100% sure that you would remember to check both, or why it's important, because it has to work for everything. So then when I put the negative 8 in here, I get negative 8 plus 7, which gives me my number to check on that side. And since it didn't work when I tested in the first situation, because negative 8 is less than 0, not greater than 0, then I know it doesn't work, so I have no solution. And then when we move on to B, we're working in log base. We need to get both of the logs on the same side so that we can condense this down so it looks like form 1. So when I do that, that makes my 2b over here by itself and just my logs on this side connected through subtraction. So I condense through division. So it's the first one divided by the second one. So I have log base 10 of x over x minus 7 equals 2. So now I have form 1, which is 1 base, so I can change it to its equivalent form. So 10 to the 2 equals the argument. So I get to this point. 10 to the 2 is 100. I need to get this out of the bottom so I can solve. So I'm going to multiply both sides by x minus 7. And so that gets me my x by itself. So when I distribute through here, I get 100x, and then 100 times the negative 7 is negative 700. So to get my x's together, I'm going to subtract 1x from both sides and move them together, which gives me my 99. And then I'm going to move the 700 to the other side. So when I divide both sides by 99, I get 7 over 99, which is a little more than 7. So as I'm checking here, it said it had to be greater than 7, and it is. It had to be greater than 0, and it is. So then the solution is at x equals 700 over 99. Okay, doing good, guys. So if we look at example 5, let's give you a second here. Pause your video and do your first read, and then do your second read. So enter the problem and mark it up, and then we will talk about what to do. So do your first and second read now. Pause your video. Okay, so we learned that we have one function f of x that has some natural logs. We have a function g of x, which also has natural logs. So right now we're all in the same base, so that's good. It says to find all the values of x. So our answer is going to be x equals such that the graph of f and g intersect. So in essence, what that's saying is that f of x equals g of x. That's what it means by when they intersect. Okay, so then to solve this problem, I'm going to do what I just said here. I'm going to take f of x and I'm going to set it equal to g of x. So that means I'm going to have the natural log of x plus 5 minus the natural log of x, and that's going to be equal to the g of x function, was the natural log of x plus 3. So now if you look at the problem, like we have been doing through this lesson, we know that here, when you're solving, the x is going to have to be greater than negative 5, because this is going to shift to the left 5. It also would have to be greater than 0, and it also has to be greater than negative 3, because this is going to shift to the left 3. So I can see that this is going to be a form 2 situation, because I can condense those down to get one natural log on the left, and I'll have one natural log on the right. So when I condense those down, then I have natural log The connector is subtraction, so that means I have x plus 5 over x. That's my argument, and that's going to equal the natural log of x plus 3. So now I can use the property of equality for logs, which says if this base log and this base log are exactly the same, then the equal sign in the middle means that the arguments have to be the same, or the x and the y, if you're going back to that original definition. So now I can equate the arguments and say x plus 5 over 5 equals x plus 3. And then this is an equation I should be able to solve for. So I'm going to, oops, sorry guys, that's not a 5. That's an x, right? Yes. Okay, and let's see, I go back and fix a couple of things here. I was just motoring right along here. So this is x plus 15 here, x plus 15 here. So x plus 15 here. All right, well, goodness, a few mistakes there. But we caught them early on, so it didn't affect our answer. So yay. Okay, so now we have properly equated the actual proper numbers from the problem itself. So that was a mouthful. All right, so now to get all my x's together, I've got an x here, I've got an x down here, I've got an x over here. I have to first get that x out of the bottom, so I'm going to multiply both sides by x. So I'm going to have x plus 15 equals x times x plus 3. And then you can see that I'm going to need to distribute here. So I get x plus 15 equals x squared plus 3x. And so as I'm looking at this problem, I should be able to see that I need to get everything together because I'm going to have a trinomial. So I'm going to have x squared, and then I'm going to move the x over here. So subtract 1x from both sides. So I have plus 2x. And then I'm going to move the 15 over there as well. So that's going to be minus 15, and it needs to be set equal to 0 to solve it. So we just moved everything over there on the same side and set it equal to 0. So now I know that I should be able to factor. What are the factors of 15 that subtract to give me 2? So that is going to be x plus 5 and x minus 3. So that means I have x equals negative 5 as a possibility and x equals 3 as a possibility. But remember, we're always checking for extraneous solutions. So as I am looking at my problem and checking here, I see a bit of a problem in the check, right? For this log, x has to be greater than negative 5. And here, it's equal to negative 5. So negative 5 is not greater than negative 5. So there's no solution that's going to come out of 5. Let me check 3. So if I put a 3 here, hold that thought for just a minute because I realize we didn't go all the way back here and check that. So I'm going to erase this real quick here, guys. Sorry, we got to the end of the notes. Maybe we're all getting a little bit of a little tired here, and I need to go back and fix this statement. So this should be, I'm moving this 15 to the left, so x needs to be greater than negative 15, not negative 5. Okay, folks, just let me hold it together for just a couple more minutes and finish this problem. Yes. All right, so then over here, when we factor, we get 5 times 3 is 15. When we subtract them, we get the positive 2. So now I'm checking negative 15. So is negative 5, I'm into this problem. So is negative 5 greater than negative 15? And it is, so that checks. If I test it here, is negative 5 greater than 0? It's not. So in this particular check here, I would say negative 15 is less than 0, so that one doesn't check. And then I'm going to test the positive 3. So if I put a positive 3, is that bigger than negative 15? And it is. If I put a 3 in here, is that bigger than 0? And it is. If I put a 3 in here, however, that's not true because I have negative, if I put a 3 in, oh, it is, I fibbed. Wow, okay, guys, sorry about that. Let's try. What's the fourth time's the charm here? My apologies sincerely. So if I put a 3 in here, 3 is greater than negative 3. So that one's going to check out. So this one checks out in all of the places of my log where I have to worry about my domain. And so from this, then negative 5 is not going to be a solution. The solution is at x equals 3. So in that case, this is the only one of those two things that has a solution. So you can have situations like we did in 4a where we had no solution because there was only one possible solution and it didn't check out. In this case, we have only one solution because one of the two solutions that we did get did not check out. Okay, so now you've seen just how many mistakes that I could make in one problem in a crazy day. Sorry about that. So what I want you to do at this point is do your first and your second read, and that way we'll have it marked up. So pause your video, do your read 1 and 2, mark up, enter the problem. We'll come back together and talk for just a few minutes, and then I will let you solve this one to practice. All right, so let's see. So we have an H equation that has a couple of log base 3's in it. We have a K equation, which also has a log base 3 in it. We want to know where all x coordinates of the point of intersections are of the graph H and K. So that means we need to know when the graph of H of x is the same as the graph of K of x. So pause your video one last time. I want you to work through this problem. Get your solutions, check for extraneous answers, and state your final solution. So go ahead and pause now, one last time. All right, let's see how you did. So I checked this. The x's for this log have to be greater than 3/2. The x's for this log have to be greater than negative 4. And the x's for this log have to be greater than negative 1/4. So move the 2 over, divide by 8. 2/8 simplifies to 1/4. All right, so now I've set h of x equal to k of x. So all of this is h of x, all of this is k of x. So that's this statement. And then I condensed because this is connected with addition. So it's this argument times this argument. So that's what I have in my log. So now this is like form 2, one log on each side. So I FOIL this together to see what the actual argument is going to be. And then I can equate my arguments because it's log base 3 on this side, which is the exact same as log base 3 on this side. So x has to equal y. And so that's what I have in the next statement. So I know that I'm solving, so I'm going to move everything over here to the same side. And so I move the 8x over, and so negative 8x plus a positive 5 gives me negative 3x. And I move the 2 over, so negative 12 minus 2 gives me negative 14. Then I factor the trinomial, which is 2x minus 7 times x plus 2. Solve each factor, so the possible solutions are at x equals 7/2 and x equals negative 2. So now I need to check these in my log solutions and make sure they work. So this one is 7/2. So 7/2 is greater than 3/2. So we're okay there. And then we're going to check here. 7/2 is bigger than negative 4, so we're okay there. And over here, 7/2 is bigger than negative 1/4. So this one is a solution. Now we need to test the negative 2. So negative 2 is not greater than 3/2. Or you could have checked here. Negative 2 is greater than negative 4. But negative 2 is not greater than negative 1/4. So you could have used either of these two to eliminate this solution, which leaves us at the only solution is at x equals 7/2. Okay, so we reviewed all of the forms of solving equations. We reviewed at the very beginning in the warm-up how to solve exponential equations, making the bases the same. So that's a lot of this carries over from Algebra 2. And we reminded ourselves that when it comes to multiple logs, we're looking at one of two forms for the solving. It's either form one, where you can condense it down to be a single log, or you can condense it down so there's a single log on either side. We're not going to fall into the trap and think that we can just mark out these logs just because they happen to be the same. And we remember that we are going to have to check for extraneous solutions whenever we solve. So then the next thing to keep in mind is, how is your answer? All of these today were exact. We did not need a calculator to solve any of them. So that's why you did not see any decimal answers. You will see fractional answers. You should be practicing these without a calculator so you can get the process and the skills down. All right, guys, take care of your DP online, and I will see you next time. Thanks so much. Bye.